So please, Timo.
Okay, thank you very much for having me and give this introduction or review on the Swampland. So I would like to structure the talk as given here by starting with some more conjectural or heuristic ideas, and then hopefully getting us to something which might eventually have the status of a theorem. Of course, as always with the theorem, the question is which assumptions we make, and there, of course, we will have to make very strong and very concrete assumptions. This will be then obviously in the context of string theory. In any event, the Swampland is a statement or is a program that tries to elaborate on properties of effective field theories in the presence of gravity. And as such, this is a program of a very broad scope. After all, as we all know, effective field theories are central objects in theoretical physics. They are the way to describe physics below a certain cutoff in all ranges of theoretical physics, from condensed matter to fluid dynamics, statistical particle physics, and of course, gravitational theories and cosmologies are no exception. Gravity, in fact, the way we describe it perturbatively, at least as a perturbative quantum field theory, is certainly an effective field theory because the quantum field theory of a two-spin particle is non-renormalizable. Hence, perturbatively, gravity is at best an effective field theory with a cutoff. The theory is hence, by definition, expected to break down at the cutoff when the theory becomes strongly coupled and new degrees of freedom cannot be neglected anymore. And in the case of gravity, this cutoff is supposed to be at least, this is at least the naive assumption, the Planck scale. So one of probably the most fundamental question in high energy physics is what replaces this effective field theory as we reach the Planck scale? And a somewhat more modest, but still very difficult and very ambitious question is, can we at least give a criterion when an effective field theory, which we observe, arises from a consistent theory of quantum gravity? So even if we may not know what the quantum gravity really is at Planck, at the Planck mass or above, can we at least tell by looking at an effective field theory, including gravity, if it comes from a consistent quantum gravity theory by dimensional reduction or not? And this is exactly the question asked in the Swampland program. In fact, according to this idea, one should distinguish between two types of effective field theories, those which are in the Swampland and those which are in the landscape. The ones in the Swampland are by definition those effective field theories which are consistent as quantum field theories, for example, anomaly free, but which are inconsistent if we describe them as theory with gravity. So they cannot come from a consistent quantum gravity as the effective field theory. Or put differently, if we want to embed a theory in the Swampland into a consistent theory of quantum gravity, we have to change it drastically at some energy scale in such a way that the theory is really different one from the one we were looking at. On the contrary, the landscape is supposed to describe the low energy effective field theories, which are good approximations to quantum gravity theory at low energies. Now, this difference between these two types of effective field theories is obviously a moving target and the subject of a number of speculations and conjectures. These are the quantum gravity conjectures or the Swampland conjectures. And these are proposals to distinguish both sides above, the Swampland from the landscape. And there are at least two approaches one can take. One could either try to make very concrete assumptions about what quantum gravity is. For example, state quantum gravity is a certain type of string theory or a certain type of or loop quantum gravity or whatever, and then deduce the consequences for the resulting effective field theories. Alternatively, one could try to find, in a more bottom-up approach, general principles which every hypothetical quantum gravity theory or effective field theory which comes from it should encompass. And the Swampland program, in fact, pursues both these different directions. Namely, first, when we try to formulate general principles with a hypothetical quantum gravity theory should encompass, even if we don't know what the theory is. This necessarily leads to, at best, speculative or conjectural statements or criteria for when a theory is in the Swampland or in the landscape. So if we work in this bottom-up approach, the arguments that are used are oftentimes heuristic. They are the subject of intense debate. Oftentimes, we don't even know why the arguments should be true, even though we have some trust in the result that will come out. Nonetheless, not everything goes. In this way, in the past years, there has arisen in the literature a growing web of conjectures, which seem to exhibit a certain degree of internal logic and consistency. Alternatively, as I said, we can now make concrete assumptions about the quantum gravity. And as a string theorist, we would, of course, try to address these Swampland questions within the framework of string theory, which, after all, is a computational framework, a very concrete computational framework. In this framework, we can try to falsify some of these general assumptions, or we can try to prove them under certain conditions. We can use what we learn to reformulate them. We can uncover the mathematical structures behind the conjectures, and in fact, can use all this as an inspiration, for example, for model building or to address conventional questions of string compactifications. And if nothing else, then this last point certainly has taken off. So oftentimes in life, one of the best motivations to really try hard to do something if somebody tells you that it's not possible to do this. And in that spirit, there has been a lot of very fruitful work invested into trying to find certain constructions which maybe the Swampland program conjectured not to be possible. And in any event, we will certainly in this way learn a lot about string theory and the construction. So these two type approaches, they influence each other in a very positive way. And this is also the structure of the talk. I will start by reviewing for you a small part in this web of conjectures and try to give some of the general arguments. And then the last part, which will be much shorter than the first part, I will address a few of these conjectures in the context of string theory and see if we can actually make actual statements of a mathematically tight type. So let's start with the first part, a web of conjectures in 4 dimensions. And I need to start first with a disclaimer. The disclaimer is that what I'm going to present is necessarily a very, very small sub-web of these types of conjectures as they have been proposed in the literature. It's by no means complete. It should really just be an appetizer. And I would like to encourage you to also to consult these 2 reviews, the review by Brennan, Carter, and Waffer, and the review by Palti, where these ideas are described in much more detail and where you can find many more and hopefully a much more complete list of arguments, ideas, and different references, certain directions, which I won't even be mentioning. And also look at the reference citing these 2 reviews, because if you work on the landscape program, then you have to sign a contract which tells you that whenever you write a paper on this landscape or the swampland, you have to cite one of these 2 reviews. And this is very practical because this way you can keep track of what happened after the reviews appeared. So these are, I think, only 350 or so papers. And if the pandemic continues, we will have time to study them all. So please do take a look there for directions of what happened after the reviews were written. And a lot happened, in particular in the last year. So this web of conjectures is a web of conjectures in 4 or more dimensions, because as we know, and this is the warning after the disclaimer, quantum gravity in 2 dimensions and 3 dimensions possibly is very different from what it is in higher dimensions. In 2 dimensions, it's a topological theory. In 3 dimensions, sort of as well. So the following conjectures are understood to be true in 4 and higher dimensions. Many of them are manifestly wrong in 2 dimensions, and in 3 dimensions, in some cases, we don't really know if they are right or wrong. The first conjecture that you all know very well, and we all know very well, is an old conjecture, namely that in a quantum theory of gravity, there should be no free dimensionless parameters, or put differently, all the couplings in the effective action of a quantum gravity should be dynamically determined as the vacuum expectation value of a scalar field, or should be the VEV of a dynamical modulus field. And this reflects a general principle of quantum gravity, namely maximal dynamical property. Everything that could be dynamical here, the coupling constant should be dynamical. Just like the metric in a gravity theory or the spacetime itself is dynamical, also the couplings should be dynamical, and therefore vacuum expectation values of fields. This is manifestly violated in 2 dimensions. So 2-dimensional worldsheet theories are examples of 2-dimensional quantum gravities. And in such theories, the couplings can be just constant. This also has to do with the nature of scalar fields in 2 dimensions. But this is not a problem. The conjecture is believed to hold at least in 4 and higher dimensions, and probably also in 3 dimensions. And obviously, it is satisfied by all effective actions that one can get from a string compactification. It might look like a very innocuous and harmless conjecture, but in fact, this is one thing I'd like to point out. If one thinks about Euclidean quantum gravity and baby universes from topologically non-trivial contributions to the path integral, then one might run into trouble. These baby universes, where a new universe kind of pops off and comes back, lead, according to Coleman, to the so-called alpha parameters in the effective Lagrangian of gravity, which would be a actual parameter in this case 4 or higher dimensional field theory. So if the no 3 dimensions parameter conjecture is true, the baby universe Hilbert space should be 1-dimensional. This was pointed out in this paper by McNamara and Waffa. And this, in fact, has interesting ties to recent ideas also in ADS-CFT. So I invite you to take a look at this paper, and a beautiful review on this problem of alpha parameters and possible relations to the swampland can be found here by Herriger, Mikhail, and Soler. The second seemingly harmless conjecture is that of no global symmetries. There exist no global symmetries in presence of gravity, or put differently, if we have an exact symmetry in gravity, or put differently, if we have a symmetry in gravity, it should either not be exact, so it should be broken by some quantum gravity effect, or it should be a gauge theory. Again, the conserved current should couple to something dynamical, hence it should be gauged. This is again this idea that everything that could be dynamical should be dynamical. And just to give one example of a heuristic argument that involves black holes, it's one of the possible heuristic arguments why continuous global symmetries should not exist. So the conjecture is more general. It also claims to be true for discrete symmetries, but for continuous global symmetries, we can run the following argument. So suppose we have a gravity theory with a continuous global symmetry. Then by definition, there must exist some states charged under the symmetry. Otherwise, the symmetry would be vacuous. So we can form a black hole by putting together many of these objects, of these charged states. And this way, one can form a black hole of, in principle, arbitrarily high charge or complicated representation, provided the group is continuous. And now one already runs into a problem. One forms, in this case, a Schwarzschild black hole. It's a Schwarzschild black hole because the symmetry by definition or by assumption is not a gauge symmetry. So the horizon and the black hole solution knows nothing about its charge. If you compute the entropy of this object, it will only depend on the area and not know about how high its representation or how high its charge under the global symmetry group will be. So this is already a sign that something's not going right, because you could, in principle, think of making an object of arbitrarily high charge without changing its entropy. So the thermodynamic interpretation of black hole entropy seems to be challenged in this situation. And the argument can be continued as follows. The usual argument is now, suppose even that the black hole starts radiating. Since it's a Schwarzschild black hole, it cannot emit any charge, any net charge by the radiation. So it will emit certain particles, charged ones possibly, but the net charge should stay the same in this way. It will emit as many positive or as negatively charged objects, if any. So this way you can reach a black hole, which will still have the same charge or representation, and whose mass will be very, very small, much smaller than the original mass. So the entropy will become even smaller than it was to begin with. And then there are two possibilities. Either we reach a black hole whose entropy is so small that for sure it cannot account anymore for the high representation or charge, or it becomes an object which is not a black hole and has a higher entropy than a black hole, a so-called remnant. And there are arguments that such charged remnants might lead to issues because of entropy violation. So this last argument is certainly heuristic and might be contested, but at least one sees that there's something going wrong in the thermodynamic interpretation of, or statistical mechanics interpretation of, the black hole entropy. In other contexts, for example, in ADS context, more rigorous arguments have been given by holography, but this is in an approach that works only for quantum gravity theories in ADS spacetime. Of course, this is good to know, but clearly we do not live in ADS spacetime, and we certainly want to understand gravity also in more general contexts. But this work here by Halo Oguri in the ADS context via holography seems to give actually a proof and quite rigorous arguments for absence of global symmetries. This theorem also looks somewhat innocuous, but it's surprising how rich it actually is, because it applies conjecturally, but according to the logic, also to generalized p-form symmetries. A general p-form symmetry is a symmetry whose charged objects are have support on p-dimensional space. So, for example, a zero-form symmetry, this would be the usual symmetry whose charged objects are zero spatial dimensional objects, i.e. particles. They exist as discrete or continuous ones, but if we look at a continuous p-form symmetry, one can also define it in such a way by saying that the conserved Noether current of this is a p+1 form, which then obeys that it's closed in the sense that d star j p+1 is 0. And one example, maybe obscure, but still an example that fits this definition, is a -1 form symmetry, as was pointed out in this paper. A -1 form symmetry is a symmetry which one gets if one has a coupling constant. Namely, if one has an action which includes a coupling term, integral over Lagrangian density lambda, times a coupling constant lambda, then this defines a conserved zero-form current as follows. First of all, dl lambda is 0 because L lambda, the Lagrangian density, is a top form. So one can dualize it to a zero form, and obviously has d star j0 is 0. So one has a conserved zero-form current in this language. So from this perspective, requiring that there should be no global symmetries, in particular no global -1 form symmetries, implies or gives back the no free parameter conjecture. And saying that this symmetry should be dynamically gauged means that we couple the current now to dynamical objects. So we promote lambda from a constant parameter to a dynamical field. So again, this idea that everything should be dynamical as possible would be perfectly consistent with this idea that the couplings are VEFs of, in this case, scalar fields. And there are even many more applications of this no global symmetry conjecture to higher p-form symmetries. For example, in the context of the cobordism conjecture, and applications to trying to classify field theories in various dimensions. And again, this is only a small subset of the papers that should be cited here. The third conjecture, also kind of a topological, no, one shouldn't call it a topological conjecture, but the third conjecture I'd like to mention is the completeness conjecture. It states that in a theory of quantum gravity with a gauge symmetry, the full charge lattice or weight lattice is actually populated by states in the physical Hilbert space. So all the states, so to every charge or to every weight vector, one can actually associate a physical state. This is different from what happens in quantum field theory. In quantum field theory, you could in principle only have operators, for example, Wilson line operators, carrying a certain representation without necessarily there being a charged particle or extended object carrying that charge. And this is, so this conjecture is also related to the no global symmetry conjecture. So for example, if we assume this, then we can show and it has been shown in one of the previous papers that some of the potential higher form symmetries are actually broken, are not conserved anymore. So there's a close relation to the previous conjecture. And it's a strong conjecture, because if one looks at a theory as innocent as, for instance, Einstein-Maxwell theory, then this theory cannot be in the landscape of quantum gravity. A theory which is only pure gravity and a U1 gauge theory without any charged matter at any energy has to be in the swampland. And at energy, the addition at every energy is of course important, because this conjecture only tells us that some state below the Planck scale should exist carrying one of these charges. It doesn't tell us at which energy scale these states should appear. Oops, where am I? Good. The next conjecture is kind of a generalization of this, if you like, or a stronger version of this. It's the famous weak gravity conjecture, which of course you all know. There's an electric and a magnetic version, and I'll start with the electric version. The electric version means that if you have an abelian gauge theory coupled to gravity, then there must exist some state whose charge to mass ratio is bigger than the charge to mass ratio of every black hole in the theory. So these states are called super extremal, because in particular, their charge to mass ratio must be bigger than the charge to mass ratio of the black hole with the highest charge to mass ratio. These are the extremal black holes. So the charge to mass ratio should be bigger than that of an extremal black hole. So the state on the left-hand side, which satisfies the conjecture, is super extremal. And again, there are a number of heuristic arguments why this should hold, but certainly no proof, absolutely no general proof. And the heuristic argument, or one of them, the heuristic arguments that were uttered originally in the original work, is that this condition ensures that every black hole can decay, and in particular, extremal black holes can decay. And if we therefore postulate that every charged black hole should be able to decay, then we get back this statement. So first of all, why is the statement necessary condition in order that a black hole can decay? This is just based on kinematic reasons. If you have an object of charge q and mass m, then it can decay into an object of smaller mass only if there exists a particle whose charge to mass ratio is bigger than the charge to mass ratio of the original decaying object. This follows for purely kinematical reasons, as one can easily convince oneself. So it is a fact that this condition here in blue is a necessary condition in order for a black hole, charged black hole, to decay. The question is, why does a charged black hole have to decay? This is absolutely not fully clear. One could argue that if all the black holes cannot decay, then again, one would form charged remnants, black holes of any possible charge. And for example, if one takes the gauge coupling G and Mills to 0, then in that limit, this would mean that below a fixed energy scale, one could have, in principle, infinitely many, as G and Mills goes to 0, differently charged black holes. And there are speculations that this again leads to certain violations with covariant entropy bounds. But this is the part of the conjecture that is debated and that is also contested. So it is not clear why every charged black hole has to decay. But if we postulate it, then this is the condition that follows, that at least one state has a charge to mass ratio bigger than that of the black hole. There is, in fact, a related way to phrase the same condition or to interpret the same condition. Namely, the condition that way is to say that the state with the highest charge to mass ratio must be such that if you take two of these states, then the repulsive Coulomb force is bigger than the attractive gravitational force on the state. Indeed, if you consider a state of charge q and charge m, you can compute the Coulomb force, and you can compute the gravitational force. The two forces will be different depending on the number of dimensions you're in. And postulating that the Coulomb force be bigger than the gravitational force gives rise to an expression, which turns out to be the same expression that you get in a theory with extremal black holes. So why would you impose this condition? You would impose this condition again to ensure that you cannot form arbitrarily highly charged remnants. Because if you take the object, the particle with the highest charge to mass ratio, such that it does not satisfy this condition, then you can take two of these states. The gravitational force now by assumption is larger, so you can form a bound state. This bound state will have a charge to mass ratio which is bigger than the one of the original state. Otherwise, it wouldn't be a bound state. And hence, since the original state had the largest charge to mass ratio, the newly formed bound state cannot decay. And you can continue, and in this way, you can get arbitrarily many different charged remnants. And if these are a problem, again, one should forbid them. The last part is the conjectural part, but under this assumption, one finds the same constraint by postulating this inequality. And this is, of course, also what gave the weak gravity conjecture its name, that gravity should be the weakest force, at least for certain states, and certainly for the ones with the highest charge to mass ratio, not for all of them. And an important extra remark, usually in the theories that we look at, for example, and that we can control, for example, supersymmetric theories, we also have master scalars around, which in addition lead to Yukawa couplings. And in this case, clearly, the gravitational force, the attractive force receives contributions not only from the gravitational part, but also from the Yukawa part. So one also has to take into account the Yukawa interactions. And these can be accommodated by this extra green factor here. The idea here is that the mass of the states depends on certain scalar fields, and then this derivative gives essentially the Yukawa coupling. So this is an easy thing to compute. But it's important if one wants to match the two types of formulations, namely the formulation of super extremality and the formulation that gravity is the weakest force. They only match if you take into account the scalar sector correctly. So in concrete applications, this is very important to keep in mind and do correctly. So the conjecture, such as I said, only states that at the very least there should be some super extremal state with whatever numerical property here we have to impose. So which types of states do they have to be? Do these have to be? And there are various versions. It becomes even more speculative now. Which particles have to satisfy the weak gravity conjecture bound? There have been many proposals, and essentially two of them have survived. The first is the Tower weak gravity conjecture. It states that it is not sufficient to have just a single or finite number of particles, which are super extremal in this sense, but there must be a tower of infinitely many such states of increasing mass. And this condition, in fact, is a sufficient condition, not necessary, maybe, I'm not sure, but certainly sufficient in order to ensure that the weak gravity, I think it's also necessary. It's definitely sufficient to ensure that the weak gravity conjecture is stable under circle compactification. So what does this mean? You could start with the weak gravity conjecture in d dimensions, and then you circle compactify to 3 dimensions. In the new theory, you have gravity, you have your original gauge field, and you also have your Kaluza-Klein gauge field. And now you're in a situation with several gauge factors, and there have been ideas how to generalize the weak gravity conjecture there. And if you want to ensure that the weak gravity conjecture is automatically satisfied in the new theory with the extra Kaluza-Klein photon, then you have to ensure that in the original theory, you have not just a single weak gravity conjecture particle, but an entire tower. This was shown in this paper. And there had been earlier considerations that had used the same argument, and that had concluded that another way, and in fact a stronger way to satisfy this, is by postulating that this tower of states should actually postulate a sublattice of the possible lattice of charges. So,
sorry to interrupt.
Please, hi.
This infinite tower of these charged particles, will you not run into the problem that at any, once gravity is turned on, at arbitrarily high mass, this will look like a black hole itself?
Well, but we don't know, of course, what the theory then would be at the Planck mass. So you would have some tower, and yes, you reach a cutoff theory where you don't know anymore what's going on. And certainly at the Planck scale, I wouldn't know how to treat these objects. So yes, you will essentially get Planck scale mass objects that need to be treated in some way.
Maybe a different way of asking the question that I was thinking earlier is that you're in a theory of quantum gravity and you're making a very sharp distinction between black holes and particles. But in a theory of quantum gravity, I mean, is this supposed to work only in the semi-classical limit or something like this? Because in the fully quantum theory, I don't know if the distinction between black holes and particles is so clear cut.
That's right. So the particles would become black holes at high energies, just like in the string spectrum, where at some stage the string states become actual black holes at very high energies. I think it would be the same idea here. So according to the sublattice version, these states should populate a so for example, in the U1 theory, you could think that you have a sublattice of states, so every multiple of 3 or every multiple of 4. This is one way to achieve a tower. And this is in fact how it is observed in all known string compactifications, but it might be too strong in general. So I'm not aware of an example of, say, a string or any known to be consistent quantum gravity theories where the sublattice weak gravity conjecture is violated, but it might be too strong, and it certainly is too strong if one only imposes this closure of the conjecture under S1 compactification. In any event, what's important is that once you reach the scale of a tower of states, your effective field theory description breaks down. This is also, of course, related to your remark. Once you are in a regime where you have infinitely many states in at a certain energy regime, this is not just an ordinary effective field theory anymore. So you expect from this a breakdown of the effective field theory in the usual way at the scale at which you reach the tower. And this tower scale is proportional to G Young-Mills. This is because the state, if you put the mass to the right, then mk squared should be proportional to G Young-Mills squared in some way. So, and then times the Planck scale. So you expect new physics at the tower scale, not m Planck, but G Young-Mills times m Planck. We said at the very beginning that the naive expectation is that the cutoff sits at m Planck. The weak gravity conjecture says the cutoff sits much lower, namely at G Young-Mills times m Planck, which can be much lower, at least if G Young-Mills is very small. This is an important first lesson. This is also called the magnetic version of the weak gravity conjecture, which can also be derived in a slightly different way. And in any event, it's something that is related to an old idea or older idea that the species, that if you have a theory with lots of particles, with a high number of particles, then the cutoff is lowered according to this formula valid now here in D equal 4 for the species scale, as described by Dwali and collaborators. And indeed, these two ideas are related, as discussed at length in this paper by Grimbheit, Venezuela, and many others as well later. Okay, so this is kind of the strong form of the weak gravity conjecture, tower weak gravity conjecture and sublattice weak gravity conjecture. There exists also a mild form, and I'm mentioning this in particular since this was already discussed on Tuesday. The mild form of the weak gravity conjecture is the one where the particles, where the objects into which a black hole should decay are other black holes. So this is certainly the form of the weak gravity conjecture valid at higher energies. The weak gravity conjecture states into which a charged black hole decays could also be black holes themselves. This is possible if the charge to mass ratio for black holes at lower energies is bigger than expected classically. So here I'm drawing from this original paper the charge to mass ratio as computed in the classical theory. And now there will be corrections to the original classical Lagrangian. There will be, in particular, higher curvature corrections, higher order corrections, f to the 4 terms in Young-Mills, and higher curvature corrections. And these will change the gravity solution and hence also the charge to mass ratio for the extremal solution. And if the sign of that correction is such that the charge to mass ratio becomes bigger for the black hole, for smaller black holes, then this would mean that the smaller black hole is super extremal with respect to the bigger black hole. So the weak gravity conjecture particle, or the weak gravity conjecture state, could be a black hole by itself. And again, this ties back into the remark that was just made, that one shouldn't really be distinguishing between the particles and the black holes. One goes into the other at high energies.
Can I ask one question? But if you had lighter particles than black holes, particles that are not black holes, but that with a charge to mass ratio, with a slope that allow the particles, the black holes to decay, any black holes to decay, then you wouldn't need to impose this constraint.
Absolutely,
right?
absolutely. So
a very weak gravity conjecture, right?
Yes, so I fully agree. So so depending on what you want to realize, all you need is a certain tower. If you is one state is enough for decay. If you believe that the black hole should decay, a tower is enough to make sure that it's closed under S1 reduction. But if you have a tower, you will, as was remarked, necessarily at some stage get into the regime where the particles become black holes themselves, and the two constraints should come out. Fit together. So I guess, and I think this is also the interpretation that most people are having in mind, that this is a manifestation of the existence of the tower, but at higher energy. So at high energy. So for consistency, this should come out, even though you would have been perfectly happy with the tower. But given the fact that a tower of particles becomes black holes, it should be consistent. And this is also probably how in string theory one should think about these high string excitations, for example. Again, there has been a large literature on this. Many papers. I apologize for not for only citing a handful here. Please consult these papers and references thereof for more information. Another generalization, and this is also something I need to mention, of course, is to higher form gauge potentials, just as the no global symmetry conjecture. Also, the weak gravity conjecture has been generalized to higher form gauge potentials. So in this case, you would have charged strings or charged higher branes. And the special case P equals 0 again is very interesting, as was the case before, because it gives rise to what was called the axionic weak gravity conjecture and studied in many subsequent works. It would mean the direct analog of this would be the statement that G squared for the axionic generalization of the gauge field, which is 1 over F, divided by the mass, which would be the volume or the action of an instanton, should be bigger than 1 over some power of M Planck. So this means that if your decay constant F in your axionic theory becomes very big, then at least some instanton should have a small instanton effective action. So should be not suppressed. And this was one of the motivations to look at this conjecture in more detail some time ago, when it came to thinking about models of large field inflation, where you would go into a very large F regime, and then you would have to battle the unsuppressed effect of some or a whole tower of instantons. And again, lots of works have considered this in detail in the past years. The fifth conjecture. So we kind of have to go through the 10 commandments here. So this is the 5th out of 10. I have to speed up a little bit. It's the conjecture called the Swampland distance conjecture, which tells us something again about the existence of a tower of states. And it's the statement that if you have a quantum gravity theory with a moduli space parameterized by massless scalars, you should always have some scalars for your your couplings, but they need not necessarily be massless. But if there are some massless directions left, then the moduli space should be non-compact, it's stated. So there should be some direction of infinite geodesic distance. And if you go in this direction of infinite geodesic distance, then you should encounter a tower of infinitely many states becoming light exponentially in the distance. So this picture here is from this nice review by Erampalti that I advertised before. It shows the expected structure of the moduli space with these directions going to infinity. And if you go into these directions to infinity with respect to the moduli space metric, you should get a tower becoming light exponentially fast, suppressed with a suppression factor that depends on an unknown constant C. The main motivation for this is, of course, unheard of. If you're just an effective field theorist, you wouldn't necessarily have a reason for this to happen at all. And I'm not aware of a very good general argument for it, other than this is what happens in Kaluza-Klein theories or in string theory compactifications. An important question for applications is, of course, the size about the suppression factor C. And according to the refined Swampland distance conjecture, it should be of order 1. And this has been tested in many works. And in fact, according to an even bolder statement, one can give a lower bound. I'll come back to this in a few slides. This is in the context of the Trans-Planckian censorship conjecture. So in general, C should be order 1. So there should be a drastic effect as soon as you reach the Planck scale distances in the moduli space. So this Swampland distance conjecture tells us that there should states becoming light, and the motivation were examples, for example, from Kaluza-Klein theories or from what happens in certain string compactifications. We will discuss this more. And if I may advertise, then there is a way to slightly make this stronger. Namely, one could propose that what type of states should be the ones becoming light at infinite distance. And the proposal is, again, based on observations and also some consistency conditions, that only one of the following two situations should occur. The states that become light should be either an infinite tower of Kaluza-Klein excitations, then this theory would decompactify, or it should be an infinite tower of string excitations, then the theory would reduce to weakly coupled string theory. So in other words, the emergent string conjecture states that at infinite distance, with whatever theory you started, gravity theory, you either decompactify and then have to think again, or you turn into a regime where you get a weakly coupled string. And in particular, these string excitations are expected to arise at or above a Kaluza-Klein scale. If they arise above a Kaluza-Klein scale, then the theory is really decompactification. If they arise at the Kaluza-Klein scale, then we find a weakly coupled string tower. So this is one way to try and characterize the theory. There is another way, independent of this, and a different with a different statement and direction, to identify the Swampland distance conjecture as an RG flow towards string defects, so to speak. I particularly would like to advertise this picture in the given reference. So there are various ideas of trying to make concrete what could be the source of the particle towers coming down in the distance conjecture. If we think in terms of infinite distances in a quantum gravity theory in ADS, it's natural to wonder what happens in the gravitational dual in the conformal field theory.
Sorry, Timo, it's 15 more minutes of conjectures.
15 more minutes?
Well,
okay, altogether.
To the hour. Yeah,
to the hour, okay. The CFT distance conjecture makes precisely the statement. It tells us what happens if we go to infinite distance now in the dual field theory, dual to an ADS compactification. So in all known examples on the gravity side, if we go to infinite distance, we reach some weak coupling theory, either a weak coupling theory where the Kaluza-Klein theory becomes weakly coupled, or a weakly coupled string theory. So it's natural to conjecture that on the dual side, all the infinite distance limits, if it exists, if the dual side exists, also should correspond to a weakly coupled field theory. And these weakly coupled field theories and CFTs necessarily have a higher spin symmetry. So the CFT distance conjecture formulates this. It's the expectation that in a CFT in d bigger equal 3, at infinite distance with respect to the Samologikov metric, you would go into a regime associated with a weakly coupled or free field CFT. So you would expect, it's in particular, expect a higher spin symmetry and an infinite tower of higher spin states. So this is a very recent development, and I think there will be many interesting works trying to flesh this out even further. Since I need to speed up a little bit, let me be quicker than I had hoped for with the remaining three conjectures. I'll just give you the statements, and I'll be happy to then discuss them more in the end. An important potential consequence of the Swampland distance conjecture is the ADS distance conjecture. So the idea is now to apply the large distance regime, the large distance motion to the metric of an ADS space by itself, rather than to the moduli. And these authors here translated an infinite distance motion in the metric of an ADS space in such a way that the cosmological constant should go to 0 from below, translated this into the statement that you would again expect a tower of states, and the tower of states, as was argued under certain assumptions, should scale like a power in the cosmological constant. And this is very interesting because it means that if you reach ADS spaces, or if you reach Minkowski space dynamically from an ADS space below, if you have such a direction, you should again lose perturbative control because states become light. So this is, if correct, an interesting consistency condition on ADS vacuum. And there's also a strong version that makes a prediction for what this coupling should actually be. Motivated by what's happening in known supersymmetric ADS vacuum. But this, at least I must point out, there are interesting potential counterexamples to this from string theory. The type 2A ADS construction by de Wolf, Gierwetz, Katru, and Taylor seems to violate the supersymmetric ADS version. And this is the subject of ongoing debate. And recently there has been a very nice paper trying to revisit this and use this as an opportunity to look again with even more interest at these type 2A constructions. So this is one of these ideas where this really serves as a motivation to look back into the string compactifications. Finally, the no de Sitter conjecture. This, of course, you've all heard of anyway. It's the bold claim that if you have in this refined version, if you have a critical point, if you have a supergravity theory with positive potential, then it should either not be a critical point, or if it is a critical point, then at least it should be a maximum. There is a long story behind possible possible derivations, also relations to the Swampland distance conjecture. I'll be happy to go through this later. And an even more bold conjecture, finally, the Transplanckian censorship conjecture states that, or it tries to give an actual reason behind the de Sitter conjecture. And the reason is that the expansion of the universe should not allow for Transplanckian modes to become classical or to ever become larger than the Hubble scale. This is very bold because it's not required by any consistency condition, as the authors stress, but it's a result-oriented approach. That's why I wanted to really bring this as an example. It's an example of a conjecture that simply by observation leads to very interesting results, which warrants already the investigation. Of course, this is by no means saying, I mean, you can deduce correct things from wrong hypotheses, but if you do something non-trivial and correct, or at least consistent, you better look twice. So one of the things that can be deduced from this hypothesis is a lower bound on the number C that appears in the de Sitter conjecture, at least asymptotically, and also a lower bound on the constant C that appears in the Swampland distance conjecture. And this lower bound, in fact, seems to be never violated, at least in the string compactifications that one has control of. So in that sense, this is rather interesting, even though one might disagree with the original hypothesis. But just to see how what the logic, or what the what the type of ideas is. Okay, so we've seen a web of conjectures. The conjectures are heuristic, but they are logically connected. The prototypical example would be, for instance, this sort of experiment which many of us have gone through in detail in their own work, is to try to deduce what, for instance, should go wrong if at finite M Planck the gauge coupling should go to 0. According to the no global symmetry conjecture, this should not be possible. So this taking G-Mills to 0 should lie at infinite distance in the moduli space, or there should be some quantum gravity censorship behind it. And the weak gravity conjecture and the Swampland distance conjecture both provide a rationale for this quantum gravity censorship. Namely, if you have a weak gravity conjecture particle tower, then if you take G-Mills to 0, the tower comes down, so your effective field theory breaks down. And the Swampland distance conjecture is precisely the same statement, just a little bit less concrete. So this is one example of a set of seemingly unrelated conjectures which become related via thought experiments of this type. And the incomplete list of conjectures which I went through here is displayed again. So, for instance, we just discussed how the distance conjecture and the no global symmetry conjecture are related. I didn't have time to tell you that the distance conjecture somewhat implies the de Sitter conjecture, at least at large field regimes. I just said that the Trans-Planckian conjecture is related to the de Sitter conjecture because it gives certain examples of the bounds to the couplings and so on. So there would be much more to say about the various relations, but just to tell you that there is some logical consistency to this whole idea. Now, last point, this is where we actually need to prove something. If you give me 3 more minutes, Fernando.
Yeah.
I'll be very quick. Trying to prove the conjectures. When we prove the conjectures, we have to make corresponding assumptions. And the stronger the assumptions, the higher the chance that you actually prove something. But in string theory, by defining your computational framework, you can do this. You can find quantitative tests. You can understand the mathematical foundations of the conjectures. And this way you can possibly even refine or unify the conjectures. And let me give 2 examples. The first is the Swampland distance conjecture for 4-dimensional theories with n = 2 supersymmetry. This is one setup where one can make all this extremely concrete. For example, these authors looked at type 2b compactifications on the Calabi-Yau 3. They looked at infinite distance limits in the complex structure moduli space. And the question was, do we get an infinite tower of states? And if so, which states are these? And the answer is yes, because if you go to infinite distance in your complex structure moduli space, what you find is that certain 3 cycles degenerate. So essentially 3 tori degenerate, become small, and so certain ratios become small. There are 3 ways how this can be done. This was discussed in great detail mathematically, much more detail than this slide suggests. If you have in type 2b theory a D3 brane wrapping a 3 cycle and the 3 cycle becomes small, then the D3 brane becomes massless. So you get a massless particle. And due to the nature of these 3 cycles, you get not a single particle, but you get an infinite tower of particles because you can wrap the 3 cycle infinitely many times. This is something special. This is something that happens only at infinite distance. At finite distance, you would only be able to wrap a finite number of times. For example, this is what happens at the conifold. At infinite distance, you can wrap infinitely many times because the nature of the cycles is different. This is what's hidden in the mathematics mathematics here, and which gives rise to this entire tower of states, which become massless exponentially fast, as was detailed in this work. So we get a tower of states. These are BPS particles. We're in 4D n equal 2. This is most control, but still interesting that one could think of. But note that these particles, their massless spectrum is indistinguishable from a KK spectrum, because this statement that Mn is n times some mass M0 is the same that you would also expect for a Kaluza-Klein reduction. So that's, from the emergent string perspective, would tell us that we are really looking at a KK reduction in disguise. These are generalized KK modes. So is there also a denser spectrum, something like a string or something even denser, which would be more important? In this approach, it's difficult to say. It's easier if we go to the mirror dual side, for example. This was done, for instance, now in compactifications to 5 dimensions on a Calabi-Yau threefold. Now we look at compactifications in the Kähler moduli space. There are again 3 types of degenerations, parallel to what we saw before. A decompactification limit, but also a limit where the volume can stay finite by some cycles in that Calabi-Yau 3 become of infinite volume. As a result, some other cycles must shrink, and these cycles are fibers. They can be T2 fibers, T4 fibers, or K3 fibers. This is what has to be shown mathematically. Again, we can find massless particles. For example, if we have a T2 fiber becoming small, we can wrap an M2 brane infinitely many times. And this is, again, gives a decompactification. Here it shows that these types of states really are decompactification states, because this is just the F-theory limit. But there can also be more complicated limits. For example, if you have a K3 fiber becoming small, an M5 brane along the K3 becomes a tensionless string with excitations. And these are the ones that furnish these denser string towers. So these string limits are manifestly seeable on this type 2A, or in this case, M-theory perspective. And quantum correct, all of this has then been analyzed in the context of quantum corrections in 4D n equal to hypermultiplet space. And we will hear more about this work by Max Wiesner later. Okay, let me summarize. There has been a web of conjectures proposed. Many of these conjectures are in excellent agreement with general predictions of string theory. I've at least very quickly told you that the distance conjecture is, if I had had more time, I would also have told you something about the weak gravity conjecture, but I'd be more than happy to do so later. Other conjectures challenge some putative string theory constructions. For example, the ADS distance conjecture in its strong form challenges the ADS, 4-dimensional ADS constructions of Gilliavets et al. And this is something very interesting. The de Sitter conjecture obviously challenges KKLT and LVS, also the Trans-Planckian censorship, in a very interesting way. And all of this is motivation to now study these constructions in more detail. Many questions are open. We'd like to push the predictions further in string theory or independently of string theory. Most importantly, we'd like to find better general arguments for some of the conjectures. Is there something like a universal conjecture, a mother conjecture from which everything follows? Something then think that it should be something like the distance conjecture. That's also why I put it into the center. But this is certainly just the beginning. Thank you very much for your attention.
So thanks a lot, Timo, for this very nice review and for the 10 conjectures that we can repeat every night before we go to bed. Are there any more questions?
I have a question. So I thank you very much for the talk. It was very clear. I'm totally very far from this field. The only work I know a little bit with this flavor is a paper by Camaño, Edelstein, Maldacena, and Cebolledo, where they put forward that you need an infinite towers of higher spins, but the hypotheses are just that you correct Einstein gravity by higher derivatives, which might be very sensible, and causality. So from your conjecture, from your 10 conjectures, I think you only spoke about higher spins in the 6th one. and the I mean the sixth or the seventh one, no, probably the seventh one. Yeah, here. So
right.
but my question is, could this work I mentioned be somehow related to this hypothesis here? The ones
I think so. Yes.
Or they should give rise to an 11th conjecture.
So was this okay? I should ask you more later. Is this if this was in ADS or in flat space?
No, it's just
in flat space. So
flat
for sure, as I think the particle tower will for sure include higher spin states. So here I made them explicitly on this page, but also the Swampland distance conjecture and all the other the states themselves will contain higher spin states. For example, if it is a string tower, it definitely has the states are definitely along a Regge trajectory. So I think it's absolutely natural to assume that this tower will include arbitrarily high spin if you go to arbitrarily high dimension. And essentially, this high spin here in the distance conjecture is precisely the dual of the string tower on the gravity side there.
My question is that nowhere you seem to talk about causality as a requirement or something like that. Whereas it's kind of instrumental.
Good.
There.
Okay, good. One would have to discuss. I cannot tell you how exactly this conjecture now will fit in. Causality, for instance, is an argument if you go back to the weak gravity conjecture. In this work, if you think of motivating this charge to mass ratio and hence the properties of the weak gravity conjecture, then one of the arguments was that you would have to impose that the higher corrections give rise to unitary and causal, no superluminal propagation, etc. theory. So these arguments have popped up, but not for the Swampland distance conjecture. Their causality as such was, to my understanding, not the motivation.
Thank you.
But it's an interesting remark. Thank you.
Thanks. Anyone? Any other question? You can speak up. You can write in the chat. You can ping Timo privately if you want later on. But do it quickly because we are on the clock.
I do a very quick question.
Oh my God, you are the next speaker.
I'm the next speaker. But I'm asking just very quick.
But there is something.
You said better on the chat. You said better on the chat or what?
No. I'm okay with any channel, but I'm worried about your next talk.
About the connection.
Yeah. No, I just wanted. Okay. No, I just wanted to know if this. I mean, these are like quantum gravity conjectures, but so most of the work is done for string theory. But I wanted just to know if Timo has a comment on that. If these conjectures, so they should be valid for all quantum gravity.
Indeed, yes. So it would be great to try and test them within other frameworks. Absolutely. So, for example, asymptotic safety. Would be nice to challenge asymptotic safety from the perspective of these conjectures, or vice versa. So, for instance, the absence of global symmetries, exact global symmetries, is I think at odds with the existence of certain fixed points that one would expect there. And I'm not aware of work trying to take this seriously in the context of, say, loop quantum gravity or loop quantum cosmology. Okay. Yeah.